Current electricity. In today's class, we learn about meter bridge and potentiometer. What is the principle on which meter bridge works? What is its description? What is its circuit diagram? How it works? And how we determine the specific resistance with meter bridge. Then the principle, working and circuit diagram of potentiometer, comparison of EMFs and determination of internal resistance of a cell with potentiometer. While working with meter bridge, we will take up a circuit and we represent the circuit connections. First, let us learn the different parts of meter bridge and the circuit diagram. Here, AB represents resistance wire and G is galvanometer, HR is high resistance, J represents jockey contact point, jockey, R represents resistance, X represents unknown resistance, C is a point on the metallic strip, and B battery resistance, then plug key. These are the different parts of meter bridge. These are the things that we come across in meter bridge. Let us discuss or describe different parts of this experimental setup. AB is a resistance wire, bridge wire. It is connected to two L-shaped metallic strips. Two L-shaped metallic strips, one is connected at A, the other one is connected at B. If X and R are not there, then there will be two gaps at X and R, and these two gaps are separated by another metallic strip. The wire, experimental wire, the metallic strips, all these are fitted to a wooden board. They are fixed to a wooden board. Now we select a resistance box, a galvanometer, a high resistance, a jockey, a plug key, and a battery. These are selected, and then an unknown resistance wire whose resistance is to be determined. The purpose of high resistance is to protect the galvanometer, to prevent high currents from passing through the galvanometer. High resistance is used in series with it. Jockey enables us to select a variable contact. We can press jockey on the bridge wire at any position. That gives a contact. So, to get a variable contact, we use a jockey. The key in the circuit is meant for off and on of the circuit. That is, to close the circuit and to break the circuit, we use key. Like this, we use different parts of the circuit. Circuit connections. Circuit connections. An unknown resistance X is connected in the left gap. An unknown resistance X is connected in the left gap. The resistance box is connected in the right gap. In the right gap, we connect a resistance box R. The battery is connected across the ends A and B of the meter bridge wire in series with a plug key. A battery and a plug key are connected in series across the meter bridge wire, ends of the meter bridge wire AB. Then galvanometer, high resistance and jockey are connected in series from the point C. From the terminal C, galvanometer, high resistance and jockey are connected in series. To verify the connections, first let us close the circuit. By using key, we close the circuit. Press the jockey at A, at the end A of the bridge wire. Then you notice deflection in the galvanometer. Then press the jockey at the position B, at the end B. You will notice another deflection. If these two deflections are in opposite direction, That is, in the first case, when you press at A, if the deflection is to the left, when you press at B, the deflection should be to the right. By pressing the jockey at A, if you get a deflection to the right, on pressing the jockey at B, you should get a deflection to the left. That is what is meant by opposite deflections. If the deflections are opposite, then the connections are correct. Otherwise, we have to verify the connections once again. After completing the connections, connecting unknown resistance X in the left gap and the resistance box in the right gap, now we proceed as follows to find the unknown resistance X. Introduce a suitable resistance which is approximately equal to the unknown resistance X in the resistance box. Introduce a resistance in the resistance box which is approximately equal to that of X. Now introduce the high resistance in the circuit and close the battery circuit. Introduce high resistance and close the battery circuit. Press jockey at A. Press the jockey at the end A of the wire. Slowly press at different points. Tap on this wire, meter bridge wire, at different points, moving towards B. Slowly move towards B by tapping at different points. Observe the deflection in the galvanometer. When the galvanometer shows nearly zero deflection, cut off the high resistance. Then you will get a large deflection. Now proceed slowly towards B by tapping. Then at one point you will notice the deflection in the galvanometer to be zero. Locate that point exactly, that is the point J. Then cut off the circuit and measure the distance AJ. Call it as L1. Measure the distance JB, it is length L2. So measure AJ is equal to L1 and JB is equal to L2 and use the following relation for finding the unknown resistance X. X by R is equal to L1 by L2. The relation that is to be used for finding X is X by R is equal to L1 by L2. That is equal to L1 by 100 minus L1. L2 is 100 minus L1. So X by R is equal to L1 by 100 minus L1. If rho is resistance per unit length, now let us find the relation X by R is equal to L1 by L2. To derive this relation, let us suppose the resistance per unit length of the meter bridge wire is rho. Resistance per unit length is sigma. Then the resistance of L1 length is L1 sigma and the resistance of L2 length is L2 sigma. Comparing the meter bridge with Wheatstone's bridge, we will have P will be in the place of X, Q will be in the place of R. P represents X, R in this resistance box represents Q, L1 sigma represents R in the resistance of Wheatstone's bridge, L1 sigma represents R in the Wheatstone's bridge, and L2 sigma represents S in Wheatstone's bridge. So substituting these values, we will get X by R is equal to L1 sigma by L2 sigma, and sigma gets cancelled. Hence the relation is X by R is equal to L1 by L2. Finding the specific resistivity of the wire and some precautions that are to be taken while doing this experiment. After determining the resistance X of the wire, stretch the wire, keep it on a meter scale and measure its length. Measure the length of the wire by stretching it on a meter scale. Use a screw gauge to measure the radius of the wire. Measure the diameter and calculate the radius of the wire with a screw gauge. Then use the relation for specific resistance or resistivity of the wire rho is equal to x by r square by L. This is the relation that is used for finding resistivity. Rho is equal to x into pi r square by L. Using this relation, we calculate the specific resistance. While doing the experiment, we have to observe certain precautions. The current in the meter bridge wire should be as small as possible. Low currents should be passed. Otherwise, the resistance will vary because of the heat developed due to the current in the wire. Current should be passed only for a short duration, not for a long time. Passing current for a long time may also heat the wire, bridge wire. As the heat is developed, the resistance of the bridge wire will not be constant. Hence, we don't get correct reading. The jockey should not be dragged along the wire. It should be tapped along the wire at different points. The jockey should be tapped at different points and it should not be dragged along the length of the wire. These are the precautions that are to be observed while doing this experiment. Use of high resistance and uses of meter bridge. Effect of high resistance in the circuit. A galvanometer is a very sensitive device. It measures very small currents. It is a sensitive device. A large deflection will be obtained for a small current in the galvanometer. So when the bridge is not balanced, there is likely a large current may pass through the galvanometer. Large current is likely to pass through the galvanometer when the bridge is not balanced, especially when we press at the ends of the meter bridge wire. So we have to decrease the current through the galvanometer. For this purpose, we connect a high resistance in series with the galvanometer. To protect the galvanometer from high currents, we use a series high resistance with the galvanometer. After attaining a near balance point, a rough balance point, we cut off this high resistance so as to obtain the exact balancing point. So high resistance should be used when the current in the galvanometer is large and should be cut off when the current through the galvanometer is small. By using a meter bridge, we can determine the resistance of an unknown resistance wire. We can determine the resistance of a wire. We can compare the resistances and we calculate the specific resistance of the material of the wire. We can also verify the series and parallel combination of resistances using a meter bridge. Potentiometer. It is a device used for measuring potential difference. It consists of 10 wires in general, 10 wires each of 1 meter in length arranged parallel to one another. The 10 wires will be so connected that they act as a single wire. They will be fixed between 2 points M and N on a wooden board. So if a current enters at the point M, it leaves the wire at N. It acts as a continuous wire. In a circuit, we will show this wire as Mn. And a jockey will be placed over this arrangement, over the bridge, over the wires. And the jockey will have knobs against each wire. When we press the knob, the jockey makes a contact with the wire. So we can get a variable contact with the jockey. The jockey can be moved on 2 rods laid parallel to one another, and these 2 rods will be laid on the extreme ends of the wires. So this is the array. Just now we have described about potentiometer. Now let us pass on to the description of connections. Generally there will be 2 circuits. One is known as primary circuit, the other one is known as secondary circuit. The top one is primary circuit and the bottom right one is secondary circuit. Mn is the potentiometer wire, Mn or the ends of the potentiometer wire. Across these ends, a battery, a key and a rheostat will be connected in series. Battery B, key K, rheostat RH are connected in series with the ends of the potentiometer wire Mn. This is primary circuit. In the secondary circuit, there will be a cell whose EMF is to be measured, a galvanometer, a high resistance and a jockey. These will be connected in series. From the end M, cell, galvanometer, high resistance and jockey will be connected in series. This part of the circuit is called as secondary circuit. So there will be two parts, primary circuit and secondary circuit, in a potentiometer experiment. Potentiometer works on the principle of opposing EMFs. Working of the potentiometer or principle involved in the potentiometer. It works on the principle of opposing EMFs. After completing the circuit connections as shown in the figure, that means after completing the primary and secondary circuits, by closing the key, if the balancing point is obtained at J and let the distance Mj, the length Mj of the potentiometer wire is L, that is called balancing length. And this is the balancing length obtained for an EMF E of the cell used in the secondary circuit. This EMF is opposed by an EMF developed across Mj. The EMF of the cell E is opposed by the EMF created across Mj of the potentiometer wire. That is why the galvanometer shows zero deflection. If these two EMFs are not balanced, then a current flows in the galvanometer circuit and thereby a deflection will be shown by the galvanometer. Let us calculate the EMF developed across Mj. Suppose the total length of the potentiometer wire Mn, resistance is say R. The potentiometer wire resistance is say R and its total length is L. Then R by L gives the resistance per unit length. Let us call it as rho. Let us indicate resistance per unit length by rho, which is equal to R by L. R is the resistance of the potentiometer wire and L being its length. The potential difference will be balanced between the rheostat and the potentiometer wire. So a part of the potential difference, EMF of the battery, will be dropped across the potentiometer wire. That potential difference, say, is V. The total potential difference across the potentiometer wire is say V. Then the current in the wire is I is equal to V by R. V is the total potential difference and R is the resistance. So V by R is current in the potentiometer wire. So the potential drop per unit length is equal to rho I. Rho I represents the potential drop across unit length. So over a length L, the potential drop is equal to rho IL. Rho IL is the potential drop across Mj developed due to the primary circuit. This potential difference is opposed by the EMF of the cell in the secondary circuit. So E will be equal to rho IL. This is the relation which we get in the potentiometer wire. Comparison of EMFs of two cells or determination of EMF of a cell by potentiometer. Comparison of EMFs or determination of potential difference EMF of a cell using a potentiometer. The cells whose EMFs are to be compared will be connected in the secondary circuit. Let us suppose their EMFs be E1 and E2. Both of them will be connected in the secondary circuit by using a two-way key. Here there is an arrow mark from the galvanometer. That arrow mark can be moved up or can be moved down. That is a variable contact. If it is moved up, E1 will be connected in the circuit. If the arrow mark is moved down, E2 will be connected in the circuit. So we can connect the required cell in the circuit. So the connections will be made. Primary circuit connections are the same. In the secondary circuit, instead of a single cell, we connect two cells by using a two-way key. First, let us connect E1 by throwing that arrow mark in the upward direction and find the balancing length of the potentiometer. Let this balancing length be L1 and throw that connection to the downward direction. Then E2 will be connected. Once again find the balancing length. This balancing length is say L2. Let L1 and L2 be the balancing lengths of the two cells E1 and E2. Then E1 will be equal to L1 rho I and E2 will be equal to L2 rho I. We have already derived the relation for EMF. E is equal to L rho I. So the EMF of the first cell E1 is equal to L1 rho I and the EMF of the second cell E2 is equal to L2 rho I. So the ratio of the EMFs E1 by E2 is equal to L1 by L2. Like this we compare the EMFs of the two cells. Instead of E2, if we use a standard cell whose EMF is constant, then we can calculate the EMF of the first cell, unknown cell E1. So like this we can compare and we can determine the EMF of an unknown cell. We can determine the internal resistance of a cell using potentiometer. We can determine the internal resistance of a cell using a potentiometer. The cell will be connected in the secondary circuit. Along with the cell, in parallel with this cell, a resistance box is also connected and a key will be placed in the circuit of the resistance box. So a resistance box and a key will be connected parallel to the cell. Then without keeping the key without connecting the resistance parallel to the cell, without including the resistance, first we find the balancing length. This balancing length is say L1. Then we are balancing the EMF of the cell when no resistance is connected parallel to the cell. So if E is the EMF of the cell, then E will be equal to L1 sigma, where sigma is potential drop per unit length. So E is equal to L1 sigma. Now a resistance is included in the resistance box and the key is closed. Then this resistance acts parallel to the cell. In this case, once again we will find the balancing length. Let us call it as L2. This balancing length L2 is due to the terminal voltage of the cell. Let us call this terminal voltage as V. So V will be equal to L2 sigma. Terminal voltage is now balanced on the potentiometer wire. So V will be equal to L2 sigma. Using the values of E and V, L1 and L2, we can calculate the internal resistance with the relation small r is equal to L1 minus L2 by L2 into capital R, where capital R is the resistance included parallel to the cell. Here the EMF E is equal to L1 sigma and terminal voltage V is equal to L2 sigma. So using the ratio E by V, we can find the relation for the resistance, internal resistance. When the resistance R is connected in parallel with the cell, then the current in the secondary circuit I is equal to E by R plus R. Now this is the current through the external resistance capital R connected parallel to the cell. that is the current. Therefore, E becomes equal to I into R plus R and V becomes equal to IR. Terminal voltage becomes I capital R and EMF becomes I into capital R plus small r. Therefore, E by V is equal to I into R plus R divided by IR. I into R plus R by IR, that is equal to 1 plus R by R. 1 plus R by R. But E by V is equal to L1 sigma by L2 sigma. L1 sigma by L2 sigma. So getting E sigma gets cancelled, so we will get L1 by L2. E by V is equal to L1 by L2. Therefore, 1 plus R by R is equal to L1 by L2, equating the two values of E by V. One is 1 plus R by R, the other one is L1 by L2. Therefore, 1 plus R by R is equal to L1 by L2. Or small r by capital R is equal to L1 by L2 minus 1. Small r by capital R is equal to L1 by L2 minus 1. Therefore, small r by capital R is equal to L1 minus L2 by L2. Therefore, small r is equal to L1 minus L2 by L2 whole multiplied by R. Small r is equal to L1 minus L2 by L2 whole multiplied by R. This is the relation. This is how we get the relation for small r. Series combination of cells. Series combination of cells. Let us take n cells, each of EMF small e and internal resistance small r. Let us connect them in series. Then these n cells will act as a single battery of EMF Ne and internal resistance Nr. The combination of n cells series is known as a battery. So this can be considered as a battery of Ne, EMF Ne and internal resistance Nr. Let us suppose an external resistance capital R is connected. An external resistance capital R is connected at the free ends. Then it becomes a closed circuit with effective resistance R plus Nr. The circuit resistance becomes R plus Nr. So the current through this circuit, external resistance, is given by I is equal to total EMF Ne divided by total effective resistance R plus Nr. Ne by R plus Nr is the total current. If small r is very, very small compared to capital R, small r is small, negligible compared to R, then I will be equal to Ne by capital R by neglecting n small r. If we neglect n small r, this can be neglected when the internal resistance is very, very small compared to the external resistance. In such a case, the current will be equal to Ne by R. If external resistance is negligible compared to the internal resistance, then the current will be equal to I is equal to E by R, that is current due to single cell with a resistance small r. So if external resistance is negligible, the current will be equal to the current due to single cell. When the internal resistance is negligible, then the current will be n times the current due to single cell. Now let us consider parallel combination of n cells. Once again, let us take n cells to be each of EMF small v and internal resistance small r, and suppose they are grouped in parallel. Then the internal resistances will be arranged in parallel. So effective internal resistance becomes R by N. Effective internal resistance becomes equal to R by N. The effective EMF becomes small e. So due to the parallel combination, the effective EMF becomes small e and the effective internal resistance becomes R by N. If an external resistance is R is connected, if an external resistance capital R is connected, then the circuit effective resistance becomes equal to capital R plus small r by n. Effective circuit resistance becomes capital R plus small r by n. So the circuit current becomes, the current through the external resistance I is equal to E divided by R plus capital R plus small r by n. E divided by capital R plus small r by n. Like this we can calculate the current through series combinations and parallel combination. Series combination is used when we want to drive a low current at high potential difference. Parallel combination is used when we want to drive high current at low potential difference. That is the difference between series and parallel combinations. Meter bridge works on the principle of Wheatstone's bridge. We know the relation is P by Q is equal to R by S. In the meter bridge, if the balancing lengths are L1 and L2, L1 against X and L2 against R, then we will get the relation X by R is equal to L1 by L2. Since L2 is equal to 100 minus L1, the relation can be written as X by R is equal to L1 by 100 minus L1. Using this relation, we calculate unknown resistance. Then we determine the length of the wire with a meter scale and the radius with screw gauge. Then we determine the specific resistance with the relation rho is equal to X into pi R square by L. R is radius, L is length, X is the resistance of the wire. Then we go to potentiometer, which works on the principle of opposing EMFs. The EMF due to the balancing length is rho IL, where rho is resistance per unit length, I is the current in the potentiometer wire, and L is the balancing length. So rho IL is potential drop across a length L. And if this balancing length is obtained from a cell of EMF E, then E will be equal to rho IL. So this is how rho IL is potential drop across the potentiometer wire. E is the EMF in the secondary circuit when the circuit gets balanced. When the current in the secondary circuit becomes 0, then E will be equal to rho IL. This is the principle on which the potentiometer works. To compare two EMFs of two cells, we use the relation E1 by E2 is equal to L1 by L2. L1 is balancing length with cell of EMF E1 and L2 is balancing length with cell of EMF E2. Then we determine the internal resistance by determining the balancing lengths with cell alone is L1. After connecting a resistance capital R parallel to the cell, the balancing length is L2. Then the internal resistance is calculated with the relation R is equal to L1 minus L2 by L2 into capital R. This relation gives the internal resistance of the cell.